Hello, and thanks for stopping by. My name is Joseph Geringer, and I'm a materials development engineer here at Essentium. Essentium provides industrial 3D printing solutions that are disrupting traditional manufacturing processes by bringing product strength and production speed together at scale with a no-compromise engineering material set. Essentium manufactures and delivers innovative industrial 3D printers and materials enabling the world's top manufacturers to bridge the gap between traditional manufacturing and machining and embrace the future of additive manufacturing. We hope that the following information will be helpful for you and encourage you to visit our website at essentium.com. The webinar will begin shortly.
All right, welcome to Essentium's live webinar. My name is Leslie Bush. I'm an applications engineer here at Essentium and will be your presenter today. Today's webinar is titled 3D Printing Applications for Thermoforming. To tell you a little bit about myself, I started at Essentium in November 2020, so I'm still brand new here, but I'm excited to be a part of the Essentium team and to develop great products, great 3D printing materials and machines for you to find the best solutions for you. A little bit about myself, I went to the Georgia Institute of Technology in Atlanta, Georgia, and studied industrial design, where I specialized in rapid prototyping and 3D printing technology. I found this futuristic technology so fascinating. I've decided to pivot and spend the rest of my career in this industry to see these technologies develop and prosper. So to get started, thermoforming. Here, let me move over. So to get started, thermoforming is a manufacturing process that is ideal for the low-cost, high-volume production of thin-walled parts like packaging for food products, containers for storage and transportation, and packaging for consumer goods like the now ubiquitous N95 mask. Year after year, we're discovering new and exciting ways to incorporate 3D printing technology into traditional thermoforming workflows. During today's webinar, I will discuss the role of thermoforming in the packaging industry and how 3D printed molds can reduce costs and increase throughput, giving you the tools you need to 3D print thermoforming tools within your ecosystem. We encourage you to submit your questions through the chat feature, and we will address these during the Q&A time at the conclusion of this presentation. This webinar is currently being recorded and will be sent to attendees for future reference. We will now begin. So the webinar overview will consist of an introduction to thermoforming, considerations for thermoforming, what are some of the parameters needed in order to quickly and efficiently create 3D models for thermoforming molds, and the plastic for both the sheet material and the 3D printing material needed for thermoforming. We'll talk about material selections, mold design considerations, and then I have 3 use cases or example applications in consumer packaging. For this first webinar, I'll be focusing mostly on consumer packaging. That's the most common application for thermoforming, and I'm highly sure that you guys have encountered thermoformed products in your life. And then finally, we will conclude. So, introduction to thermoforming. Thermoforming is a widely used manufacturing process where thin sheets of plastic are heated uniformly and draped over a mold. A vacuum is then applied to remove air underneath the sheet, suctioning it to the mold and allowing it to take shape. Flash is trimmed in a secondary process. So this video we see here is an example of several one sheet molds being vacuum formed. Basically, you take a heated oven, apply heat to the plastic substrate, it's draped over, and then vacuum is suctioned in order for the material to collapse around all the contours of the mold. Thermoforming utilizes low vacuum suction, so relatively inexpensive aluminum molds are typically utilized. This process is capable of both low to high volume production workflows. High production thermoforming is even more efficient when multiple parts are incorporated onto a single former. So this is an example of an industrial thermoforming. Excuse me. Okay, good. We have that working. So this is an example of an industrial thermoforming workflow. You can see multiple machines and multiple presses with either male or female forms, or a combination of both, pressing down on the sheet substrate in order to quickly generate tons and tons of final products that can then be cut and removed, and then air ejected from the mold in order to be removed from the assembly line and getting ready for packaging and assembly. So with thermoforming, we have a wide spectrum of low to high volume production. For low volume thermoforming procedures, we use wood, MDF, or plaster of Paris to create the body of the thermoformed mold. These are cheap, they're easy to use, machine, and they're ideal for prototyping and very short pull cycles. However, they have a low lifespan. So after repeated use of heat cycles, vacuum suction, and the shrinkage that the sheet of material will apply to that mold, the mold would often deform after several uses. So these really aren't ideal for end use parts. They're more for prototyping and quick iterations. For medium volume production, the molds will typically be coated with a type of epoxy or made out of aluminum. These allow for good durability when properly made. For the epoxy models, that's a high temperature resistant epoxy that can withstand temperatures up to like 200 to 300 degrees Celsius. And also heavy gauge production of thermoforming parts can range from 250 to 3,000 units a year. Heavy gauge thermoforming, that's basically just saying, referring to the thickness of the thermoforming sheet, is lower in production, and those are usually for permanent installations, like products that you would see in cars, like cars and fixtures, and maybe even wall panelings. For high volume production, the mold material is almost always aluminum. It's moderately expensive, requires longer turnaround times, but requires very low maintenance, and the longevity of those aluminum molds are pretty good as long as you maintain the proper heat cycling parameters. These consist of mostly thin gauge or thin walled thermoformed parts, and the production of these parts for high volume production exceeds 3,000 units a year. So some common applications for thermoforming, I can highly assure you that basically if you're alive, you have encountered a thermoforming part. The ubiquitous solo cup, the red solo cup, and even the solo coffee lids, those are thermoformed products. So take a look when you're in your kitchen next, or if you're at Starbucks, and most likely you will see some of these thermoformed products. They're great for food and beverages. If you select a food safe material, of course. Automotive is also utilizes thermoforming for interior paneling, say for like the coffee holders in your car, the walls, the dashboard panels, and what have you. Consumer goods packaging is extremely, or thermoforming applications are extremely prevalent in consumer goods packaging. So you have toys, electronics, pretty much anything, like anything that has a plastic case or a plastic container, most likely has been thermoformed. But you also have signage and wayfinding. So for large internal or external signs, thermoforming is a great way to quickly produce and cheaply produce visually interesting signs that could then be vinyled on top, painted, and any like particular branding can be added to that thermoformed part. Next, we have medical. So say like Invisalign aligners or those types of clear invisible braces are thermoformed as well, but in much lower quantities and used to correctly articulate your teeth into the right orientation. Lastly, we have decor and interior fixtures. So bathtubs are actually thermoformed as well. Those are higher gauge thermoforming procedures, but It's a very quick, easy way to make large parts, and they can be easily processed. The tooling is less costly than other types of traditional manufacturing, like injection molding. So it's a great opportunity to use to quickly iterate and produce large parts. So to go in depth on the vacuum forming or the thermoforming process, thermoforming is actually an umbrella term for a couple of different processes. You may have heard of vacuum forming. That's one of the most common types of thermal forming to produce plastic thin walled parts. If you see in the GIF here, we have, say, a fabricated mold. It could be a male or female mold. It's typically one-sided for vacuum forming procedures. You have a heater, almost like a convection oven heater at the very top, or a series of coils that will heat up a sheet of plastic to its heat deflection temperature. Once it sags and deflects a bit, it's now malleable enough to be draped over and to be formed into a part. So the vacuum suction also helps to form the part. Once that's quickly cooled, it'll be ejected and popped off the mold very easily. One thing you can notice, this kind of looks like a cake pan. Thermoforming requires the use of draft angles for easy part release. I'll talk about that a bit more later. And so for one example here, this is still vacuum forming, but want to emphasize that for traditional vacuum forming molds, there's actually vent holes, say for sharp corners and along flat surfaces especially, in order to help facilitate and move along the airflow from underneath the draped material. So you can see for sharp details like this, it's ideal to have venting holes that would be located on the bottom of the mold. Next, we'll talk about pressure forming. So that's a different umbrella term for a different thermoforming procedure, in that you're not pressing, you're still pressing the sheet substrate into a mold, only air pressure is coming from above and pushing down on the molten, or I'm sorry, on the flexible material in order to conform it to the thermoform shape or to the mold shape. Next, we have plastic twin sheet forming. So that is ideally used for kind of more paneling installations. You'll see twin sheet forming with heavy duty gauge materials as well. So they're a bit stronger, a bit more costly, but it used in shorter runs. And this is where you take two twin sheets of material. They're both heated at the same time, at the same temperature, until they're pliable and flexible, and then contorted into a male and female shape. Lastly, we have compression molding. So this still requires the utilization of plastic, molds, and air pressure, only you have what's called a charge, which is a molten blob of material that's inserted into the mold, and then that is then pressed and conformed into the final part. So next, we'll talk about considerations for thermoforming and 3D printed mold design. Talking about how 3D printed mold design differs from traditional aluminum mold design. Just getting my computer in alignment. All right, so the first thing to talk about is complexity is free. So this is an actual term that's thrown around very frequently in the additive manufacturing industry. So what this is saying is 3D printing, or also known as additive manufacturing, typically allows the user limitless geometric complexity and design freedom. If you have a 3D model of a part, most likely you can 3D print it. However, when you're designing for thermoforming, you are constrained by the thermoforming process. There are considerations that need to be taken, since you're creating a marriage between 3D printing and thermoforming, which is a traditional less flexible thermoforming procedure, but it's still a high volume, valuable industry to delve into. If we look at the chart, we can see on the x-axis, we have geometric complexity, and on the y-axis, we have manufacturing costs per piece. So as for 3D printing, as the complexity of a part increases, you don't see any increase, or even you don't see any increase in the manufacturing cost, whatever the part is or whatever the geometry is. All that really matters is the print time and the material usage. You don't see a rise in costs per part. However, with traditional manufacturing, say like creating metal molds for injection molding or thermoforming, as the mold gets more complex, as you add additional features and tooling paths, that does add considerable amounts of time and costs to the manufacturer of the whole entire part. So when you're making 3D model designs, some of the constraints and considerations you need to take into account is 3D print porosity and vacuum venting, the draw ratio. So that's ensuring that you have the right amount of sheet material and thickness to allow the sheets to stretch, contort, and form over the model. Draft angles are required, like the cake pan or cake molds metaphor I mentioned previously. Having not vertical angles, but kind of slightly tilted angles on the sidewalls allows molds to easily be released. And in the manufacturing process, usually a mold release like silicone spray is applied to the molds to help facilitate the plastic part from being popped off and easily released from the mold. Also, undercuts are typically discouraged in thermoforming. Undercuts are, I'll have a slide going into some of these topics coming shortly. So undercuts require additional cam actions, which would have sliding actuated parts coming in from the left and right, or perhaps top and bottom, in order to facilitate any overhangs or undercuts. So that adds time and complexity to the mold. And also, you may not get the best results. Next, we have rounded edges and corners. For the best mold release, it's good to have filleted and rounded edges to prevent any uneven thinning of material when the material is being draped over a part. Next, we'll talk about walls and infill and layer height. And those two are applied when creating 3D printable G-code. And each slide going forward, we'll talk about these features in depth. Okay, so talking about 3D print porosity and vacuum venting. So Essentium's 3D printers, also known as high-speed extrusion 3D printers, use what's called extrusion-based 3D printing, where you take thermoplastics, like thermoplastic filament that's heated up to a certain temperature and extruded through a nozzle. So you can get, when the nozzle deposits these layers, it allows for strong interlayer bonding, but the beads of material that are being deposited through the nozzle are oval-like when you do a cross-section of them. If you notice the diagram on the left, you can see the cross-sections of a 3D print. And each bead is laid up next to each other, both horizontally and vertically. However, there are some gaps between each one of these bonds, and so that actually creates small voids or pores within the part. This is actually extremely valuable for vacuum forming because it helps to facilitate the flow of material, or the flow of air, I'm sorry, through the part, allowing for easier suction of the plastic substrate onto the mold. So with this, you actually don't need to do any post-processing, like drilling holes into the 3D print, or actually adding holes into your 3D model and then 3D printing voids or through holes. So that's actually reduces printing time and still allows you to get very strong molds without the need for these venting holes. So next, draw ratio. When thermoforming, a sheet of plastic is drawn or stretched over a mold. Calculating a draw ratio is based on the mold geometry and will help you determine what thickness of plastic is needed for proper molding. For thermoforming, they use predominantly thick gauge and thin gauge sheets of material. So thin gauge can usually range from like several millimeters, yeah, about several millimeters for thick gauge, up to like say 1/4 inch to half an inch of material, depending on the application. Plastic that is too thin can tear when overstretched. Plastic that's too thin will also add excessive, oh, I'm sorry, plastic that is too thick will add excessive bulk and cost to your process. Additional heat will be required to properly stretch over intricate details if you're using very thick material. And in this example, this is a great example of a very thin, a complex mold that has been stretched over with a very thin sheet. So you can see like in the cups on in each cell, they're a little bit transparent. That's because the material has been stretched unevenly to fit those areas. So while you do have a completely enclosed and molded sheet, those will not be as strong as other parts of the mold and could tear and pretty much be useless as far as packaging and durability is worth. As a general rule of thumb, you want your mold height to be less than the mold width. So basic formulas for calculating a draw ratio include dividing the surface area of the part by the footprint of the part. And then with that draw ratio information, you can then multiply the draw ratio by the desired finishing gauge to create your minimum starting gauge. So in order to figure out what thickness of material you want to use, you multiply the draw ratio by what your endpoint thickness should be for your part. Next, we'll talk about draft angles. So draft angles are crucial and essential to successful 3D printed pulls when you're removing the sheet of material from a mold. In this example, this is one of my applications I created for this webinar. It's a set of, it's a tray to hold wireless earbuds. Some of the examples I'm presenting to you guys are things I pulled from my day-to-day life, things I encounter very frequently, in order to keep things interesting. So this is actually 2 wireless earbuds that are combined by a cord and has a little like volume control on the left-hand side. So when you're designing in a CAD software such as SolidWorks, which is ideal for manufacturing, they have a tool called draft analysis that allows you to identify surfaces requiring a draft angle in order to achieve a successful pull. Too small of a draft angle may make the plastic sheet difficult to pull up and away from the mold. For industry standards, they typically recommend a 1.5 to 2 degree draft for vertical female parts, or for vertical features on female parts, and a 5 to 6 degree draft for vertical parts on male features. And in certain cases, you can have a 0 degree or even a negative draft, but that's very dependent on the geometry, the severity of the negative draft, and what particular sheet material that you're using. Like if you're using material that's not pliable enough or isn't heated to the right temperature, it may not be flexible enough to actually perform those negative drafts successfully. It could potentially break the sheet of material. See, so for when using the drafting analysis tool, it will actually color code various areas of your mold. You'll select the direction of the thermoforming pull. So in this case, the pull is going to be perpendicular to that green face and be pulled upwards. You input the desired draft angle to filter the results, and then the results will show a color code feedback of areas that have a positive draft, areas that require additional draft to achieve the draft that you need, or will have a negative draft. In this example, I want to ensure that my sidewalls have a 6 degree draft in it. In the diagram, these currently have 0 draft, so they're showing as yellow areas that require draft. Oh, sorry, you guys, I'm using 2 monitors and it's being a little tricky today, but I hope you can bear with me. Sorry, just one second. There we go. Okay, so in addition, after you've applied draft analysis, you know exactly what areas you need to target for your mold, and then you could go back and model or make adjustments to your model and increase that draft angle to the sidewalls. So there's actually a tool called draft angle, which will then allow you to select, say, all of those vertical surfaces and put your desired draft angle, as well as selecting the neutral plane, and then select apply to apply the draft to those vertical surfaces. Very quick and easy. So next, we'll talk about undercuts. So undercuts should not be present in the thermoforming mold unless essentially you know what you're doing. Undercuts and overhangs will snag on the plastic sheet and prevent the sheet from quickly and easily releasing itself from the mold. It could damage the mold upon the release, and depending on certain geometry, sheet gauge, and sheet material, it is possible, but you have to plan for it. So in this example, I went ahead and just cut a divot or inset into the side of my mold, just as an example, so you can visually see, what this undercut or overhang would look like in the model. So you can see here. And so when using the undercut analysis, it works in the same fashion as the draft analysis. It'll color code areas that are undercuts, basically. So if that's something that you want to include in your mold, just know that additional machine actions would need to be taken. Say like a side cam action would need to come in and slide underneath your mold in order to actually form part of that, that undercut. And so here we can select, what the direction of the pull is. Once again, we can select, what the neutral face is of this pull. The neutral face for this, again, would be the top surface. And here in red, we can see an included undercut. And in the kind of light blue or grayish blue, we can see, a typical or direction 1 undercut. Next, we'll talk about rounded edges and corners. So sharp corners in thermoforming can lead to issues when demolding your part. The sharp corners can cause excessive thinning when the sheet is being draped and vacuum pulled over the mold, and that actually could lead to tearing. So it's always good to apply a radius or a chamfer or a combination of both to your mold in order to help ease and facilitate the release of the part. Next, we'll talk about walls and infill. So these two are especially or are tied to the G-code production for 3D printing. So if you're not familiar with G-code or the slicing process, this is where you take a 3D model, say something that was developed in SolidWorks or any type of other CAD package, and then basically you're applying different printing parameters in order to create actionable and executable code that a 3D printer can read. So this is actually pulled from a slicing software that we use internally. And here we can apply how thick you want the walls to be, and the type of infill or kind of honeycomb internal structure that can create a model that's dense or that's very dense with, like, say 100% infill, so it's completely solid, or with very sparse infill where there's like a very large kind of honeycomb structure inside that allows some gentle support. So ideally for thermoforming, because you're applying both pressure and heat, while for short periods of time, you want the mold to withstand for multiple pull cycles. So ideally you want a stronger or a higher wall to infill ratio. So if we're looking at this part, the kind of turquoise sidewalls that you can see in this diagram, those have additional walls, or those are the additional primers. So the 3D printer nozzle will create multiple tool paths and create those very thick walls. So essentially you're getting kind of like a thicker shell surrounding that honeycomb center. So these are concentric tool paths that will create a solid shell. Say, for instance, if you want to do some secondary machining on these 3D printed molds, you actually would even further increase the wall thickness so that you have solid material to mill through. So one interesting note is for high-speed 3D printing, it's good to actually use more printers like this than to achieve strong parts rather than using and relying on infill. However, if the walls or the shell of your model is too thin, the excessive heat and pressure on the mold can actually cause the infill pattern to be highly visible on your final sheet substrate. So unless for some reason you want to have kind of like a honeycomb like structure imprinted onto your thermoformed part, you definitely want to have strong and durable walls. Next, we'll talk about layer height. So anything that's 3D printed, or say for current commercial 3D printing technologies, will rely on consecutive layers stacked on top of one another. And so you'll begin with the first layer, then the bed will drop down and print and deposit a second layer of material, and so forth. The stair-stepping effect can be present on certain geometries if you're using really thick layers. So think of them as stair steps on a sloped surface. If you look at the picture on the left, you can see that stair stepping in action for one of the molds I designed. I intentionally 3D printed it with a larger nozzle. The HFC machine uses 0.4 and 0.8 nozzles. That's diameter 0.4 to 0.8 relates to the orifice at the very tip of the nozzle where the material is being extruded. So ideally, if you want to have very clean and smooth layer lines, or clean and smooth surfaces, excuse me, you want to have thinner layers so that stair stepping is less pronounced and you have smoother transitions along sloped walls. Also, thinner layers means little to no need for post-processing smoothing. You don't have to sand these after the fact. You don't have to apply epoxy or say Bondo, any type of material that would be used, or say like a secondary post-processing technology like vapor honing, where you're actually kind of melting the surface of material. You can use these right off the bat if you use a thinner layer height and a smaller nozzle. So these thinner layers are less likely to be imprinted onto the sheet substrate. Oops, it's getting away from me. All right, next we'll talk about thermoforming sheet materials and some of the most common sheet materials used in thermoforming and our choices for selecting them for your thermoforming use case. So certain parameters you'll think about when selecting a sheet material is the cost of the material, the sheet gauge. Is this going to be a thin gauge or thick gauge application? What is the pliability at relatively low temperatures? You want to know what the heat deflection temperature is. The heat deflection temperature is to know what temperature you need to heat that sheet of material, and also use that information to select an appropriate 3D printing material that will melt. You want to have very strong mold. Next, if chemical resistance is something that's needed in your final part, you want to choose a sheet material that has chemical resistance and has a high level durability. Also, if you need like water barriers or something food safe, those are things to articulate into your design procedure as well. So there are so many different thermoplastics that are great for thermoforming. I'm just selecting some of the most useful and most common. So starting with ABS plastic, it's an engineering grade material with UV and impact resistance. Acrylic, it's inexpensive, but can be brittle, and with high UV and chemical resistance. It's not suited for tight bends and fine details. So if you're thermoforming something that has a lot of contortions, maybe even an overhang that you might apply with some cam actions inside, acrylic would not be a good choice because it has less of a likelihood to be able to properly thin or properly bend to those overhangs. Next, we have HDPE, which has high impact strength, and it's great for industrial applications. Some of the most common materials that we'll see in consumer packaging are HIPS and PETG. They're both relatively inexpensive, lightweight, and great for food packaging and enclosures. Definitely the food safe is the best way to be, and they're easy to recycle. Next, we have polycarbonate and polypropylene sheets. Both are also engineering grade materials. Polycarbonate is difficult to conform to details, and also it has a higher heat deflection temperature, which means it does require more heat in order to become pliable and moldable. Polypropylene has a high chemical resistance and is also food safe. So there's no one size fits all material, but there's definitely lots of options, some that aren't featured here, for your best use case. On this slide, we'll shows some of the common thermoforming materials that I just discussed, and also what their typical thermoforming temperatures are. So if we look at, for example, polystyrene, that's also another very common thermoforming material. Thermoforming temperature can range from 150 to 109 degrees Celsius, and a maximum draw ratio of 8:1. So one of the very important things to pull from this information, of course, be the draw ratio, but also the thermoforming temperature, because this is going to directly affect, which I'll show you shortly, what 3D printing material to select. So for example, if you have, say, what's some of the highest? So polycarbonate, like I mentioned before, has one of the higher thermoforming temperatures. So if it has a working temperature of 175 to 230 degrees Celsius, you definitely want to select a 3D printing material to 3D print your mold with a temperature that exceeds 230 degrees Celsius. Yes. Next, we'll talk about 3D printing material selection. Okay, so with extrusion-based 3D printing, say for the technology that Essentium uses, we use thermoplastics. There's two different categories, semi-crystalline and amorphous. So the difference between the two of them is their molecular structure. Amorphous materials are actually, in a way, easier to print because they have a wide print, say like printing window. There's kind of a large window of temperature between at the point where you reach like the heat deflection temperature and the glass transition temperature. However, for semi-crystalline, you have a shorter selection of heating temperatures that requires a bit more time and consideration and more accurate temperature control. So in a way, amorphous materials are a bit easier to print with versus semi-crystalline materials, but there are benefits to both of them. They both could be either cheap and commodity-like materials, or they both have high performance options. So some of the other considerations for 3D printing materials are the heat deflection temperature, which is at what temperature can that particular material start to deflect. We have self-lubricating and low friction plastics. So that might be something to consider if you want to print a very high volume mold that would need that would also facilitate the quick release of your plastic substrate. Self-lubricating or low friction materials like nylons might be a great option. Next, we have degradation temperature. That's at the point where the material starts to burn and could potentially combust, and that is the temperature that we definitely want to avoid. Next, we have vacuum pressure. Like I mentioned previously, thermoforming uses low pressure. So ideally, a lot of these engineering and high performance materials will work just fine as long-term molds. So this is definitely an important slide to pay attention to. This is heat resistance. Talking about, okay, will the material be at an elevated temperature for long, short periods of time, a few days versus a few minutes? For thermoforming, we only need heat resistance for, say, like up to several minutes at a time. in order to thoroughly heat the large substrate. So, based on the short period of time, and also what temperature you're heating your sheet substrate is, you can then select a range of appropriate materials. If you're using a sheet material that probably exceeds, or I'm sorry, if you're using sheet material that is pliable, like around 200 degrees Celsius or less, PA, PEEK, HTN, HTNCF, PSU, and PI could be great options. And so from that particular quadrant, I selected materials for my use cases. And so here, I'm demonstrating, or I'm showing you the 4 different materials I printed my use cases for, or with, excuse me. Oops. My monitor is not cooperating. All right, here we go. Okay, so the first option is PETCF. It's a polyester filament loaded with 15% carbon fiber. It's very easy to print, strong, and affordable. And what's also great is it can be annealed after printing in order to increase the temperature resistance up to 155 degrees Celsius. Applications include tooling, functional prototypes, automotive parts, and housings. Coming up next, we have HTNCF. So this is a high temperature nylon. HTN stands for high temperature nylon with a 25% carbon fiber reinforced core. So this is actually Essentium's strongest, or has the highest strength and stiffness ratio in Essentium's 3 printing library. It's easy to print, and it's great for replacing tools and light duty aluminum parts. So this actually is like one of the best materials that we have for thermoforming molds, and it has a heat deflection temperature of 182 degrees Celsius. Next, we have PACF, which is also a type of nylon, which is loaded with carbon fiber, and is also easy to print and great for industrial applications. It has a heat deflection temperature of 178 degrees Celsius. Last but not least, we have Essentium 9085. It's a PEI material, and it's made with Sabic Ultem 9085 resin. It's all around amazing material that has excellent temperature, toughness, strength, and stiffness. It's also flame retardant. It has a heat deflection temperature of 152 degrees Celsius. All right. So finally, I will be talking about my 3 use cases for thermoforming. So since this particular webinar is focusing on consumer goods packaging, I selected a couple different consumer goods and 3D models and did test polls for them for you to see. I'll show you some process pictures. For these short runs, I use a DIY jig that we have in-house, but for future iterations and development, I definitely will be looking to outsource these procedures and to get some additional data. So consumer electronics has definitely been utilizing thermoformed packaging for decades. And in more recent years, you're actually seeing consumer electronics create very almost like cute and visually interesting trays to bundle their product in. You can also find them in just commodity items like batteries and light bulbs. So we see this photo here. So this is my 3D model of the wireless earbuds. And so to talk about the build statistics, the dimensions are 106 by 186 by 33 millimeters. The material I selected for this use case is PETCF. It had a print time of 6 hours and 51 minutes, a plastic weight of 120 grams, and the 3D printed tooling cost. This tooling cost includes the cost of material, machine time, and operator or employee cost. So the cost for this 3D print tooling is $225. In the comparison quote for equivalent aluminum tooling for thermoforming, we have $3,421 with a turnaround time of 1 week. So here you have a cost savings of $3,000, $3,195.57. So here we can see some of the, the procedure or the jig I use to thermoform. So this was actually a CNC'd frame or a CNC'd out of plywood, and it's great for very low run prototype pulls. So the tools I used, I clamped down a sheet of PETG clear material. I taped the mold down to the vacuum form bed. You can see that has like a perforated board consisting on the bottom. And so that's actually tied to a shop vac that will then pull and draw in any excess air when we heat up and drape the sheet material over the mold. Oops. Oh, my mistake. Pardon me, you guys. Somehow I decided to just, I'm done. So I decided to just exit out of the presentation somehow. Let's get that back up for you. Here we go. All right, so here's another photo of my setup. We have the HVAC or the shop vac attached to the thermoforming jig. We have our mold on top, and heat will be then applied. So we have a heat lamp on top here. If you see this dusting, that's actually talcum powder. It's great as like a DIY mold release for thermoforming. For long-term molds and pulls, it's better to use kind of like an industrial silicone mold release spray. So applying uniform heat to the sheets by like waving the heating lamp over the sheet material, pressing the pliable sheet down onto the mold, and then turning on the vacuum, which results in your fully pulled mold. You can see here, then I trimmed the excess, and we have the resulting mold here. And like I mentioned before, so some defects that can come from having too thin walls includes the perforations or the internal infill showing up in the final result. So if that's an aesthetic that you're looking for, it might even be better to add complexity to your 3D model while still maintaining like even thicker layer heights. You could 3D model textures onto your mold and then add additional perimeters to your mold so they don't collapse after sustained heat. So next example, we have food packaging applications. So if you indulge in chocolate like myself, or if you drink a lot of coffee or eat lots of baked goods, you're definitely familiar with thermoformed packaging. They're not just for desserts, but I love dessert, so this is what I'm focusing on. So in the food packaging chocolate box, so it has an overall volume of 215 by 215 by 32 millimeters. The material I selected was PACF. The print time was 13 hours and 7 minutes with a plastic weight of 289 grams. The total 3D printed tooling costs for this chocolate box frame, it's a nice little tray, is $409. The equivalent aluminum tooling cost is $2,340 with a 1 week turnaround time, giving you a cost saving of $1,000, $1,931. And I actually printed 2 different chocolate molds. The second one was printed in HTNCF, because I mentioned before, that's an all-around great material to use for for thermoforming applications. Same print time, same material weight. The only difference is the cost of the material itself that's being factored in. So you get a slightly higher tooling cost, that's $430, but you still get significant cost savings and fast turnaround time. So you can see, like a more detailed photo of the chocolate box with detail inside the cups at the bottom. So that would require a higher draw ratio in order to achieve desirable pull results. So you can see here the pull on the left, and of course, remember this is a kind of like a ad hoc. So a lot of this is manual process. So for this example, it's actually great for you to see that the draw ratio wasn't quite right for this sheet of material and the mold combination. So ideally, for future development, a thicker sheet material would be used. For our last use case, I'm going to talk about the N95 mask for consumer goods packaging. So the global N95 medical protective mask market, the revenues projected to surpass $1.58 billion by 2027, according to a new study by President's Research. So if you're like me, we're all going through the COVID-19 pandemic together. I personally have not seen an N95 mask in shelves for over a year now. I don't know if you can see the one I'm holding up here, but this is one I've basically saved for emergency situations for the past year. In typical situations, these were prevalently used, in medical and certain hospitals, but also for dust management and proper respiration if you're doing a lot of sanding, painting, and what have you. So these have been flying off the shelves since, well, the United States since February or March of 2020. And so I really found this to be an interesting use case because consumer trends are changing as the pandemic has been going on for the past year. In this study, or the survey, we saw a production of 45 million units of N95 masks in the United States. The graph on the left shows production from January 2020, and then as the pandemic progressed, that production has jumped significantly to 180 million units, which is pretty outrageous. So, of course, this is a very highly demanded product. In turn, the demand for sheet material and packaging solutions and molding solutions for this mask in order to get it out to first responders and those vulnerable and high at risk for contracting COVID-19. So I thought this definitely was a use case I want to pay some particular attention to. So for the mold, it's roughly the size of my face actually, dimensions of 198 millimeters by 182 by 57 millimeters. You can see here. And this is printed in Essentium 9085, which is the all-around great and durable material that's also has innate flame retardant capabilities. And it has a very short print time. This is the one where I intentionally printed with a larger nozzle, so you can see the striations. It's probably easier in the visuals I showed, but at least you can see it here too. I'll back it up a little bit. So the plastic weight was 359 grams with a tooling cost of $216. The equivalent aluminum tooling cost was $1,757 with a turnaround time of 1 week. So that week is crucial when dealing with the pandemic situation, when trying to generate and meet up with over demand for this product. Turnaround time and throughput is absolutely crucial. So even ideally for creating larger volumes of these N95 masks, you would create a mold that has multiple male parts in one mold, so you can increase the volume of your production significantly. But for this demonstration, this is just a simple first phase of the mold. here's a cross section, same information as before. I'm just showing you the number of walls, probably about 10 walls. You definitely want to have, you know, like more, like almost like half an inch of wall thickness to your models if possible, in order to get good strength. And this, I specifically chose Essentium 9085 for its overall strength and longevity and toughness. So we can see a photo of the finished part in Essentium's HSC 3D printer. See the talcum powder applied thoroughly to the mold for easy release. The final pulled part. And for context, you know, placing the N95 mask into the plastic packaging. So to quickly wrap up, because I want to make sure I have time to answer some questions. 3D printing applications for thermoforming can increase your turnaround times in comparison to traditional machined aluminum molds for high demand consumer goods like N95 masks and different commodities that become increasingly valuable during the pandemic. Time is crucial. We have a large portfolio of 3D printed materials to complement each specific mold design and plastic substrate utilized. You can also manufacture affordable, high volume molds. So a quick disclaimer, I'll be hosting our next webinar in April, component masking for PCB conformal coating. So we'll be talking about printed circuit board production and how applying a thin layer of protective material can prevent short circuits and degradation in PCBs. But we use special 3D printed ESD boots to place over surface mounted components in order to mask those off that don't need that film or protective film on them. So the registration link is below. This webinar is being recorded, so you'll have access to this registration link. And you can also check Essentium's webinar website to see previous recordings. This recording will be placed there, and information about subscribing to the next webinar. I want to thank you guys for your time, and I want to give you some time. I know we're running a little late, but if you have any questions, feel free to type them in right here. And also to mention, the next coming webinar is April 14th at 10 a.m. Central. Okay, let's see. One question I have here, what would be the number of cycles the molds could withstand? So that's a very good question. So that is actually going to be one of the next tasks that I can have verifiable data for you. These molds, I only did a handful of pulls at a time, but 3D printed molds have already been in use for, or it's become more prevalent in thermoforming. So there definitely are use cases, I would say, definitely in the low to medium volume quantities. High volume would take some additional testing on our end. I would assume using Essentium 9085, also known as PI, would probably be the ideal choice for high volume pull production. Unfortunately, I don't have a number for you right now, but definitely stay tuned with us, and that's something I'll be researching in the future. And another question, yes, so the prints are porous innately, just due to the 3D printing technology itself. The extrusion-based 3D printing technologies, they have interlayer bonding, but as I showed in the diagram, I can actually go back to that slide. Let's see, as I go back to that, there are voids within the part innately, so that actually allows you to have porous models without the need for vacuum holes. So that still allows for ideal air movement for your thermoform molds that are 3D printed. Excuse me. All right, let's see what other questions we have. All right. Yeah, I think we might have covered everything. So if you guys don't have any additional questions for me, that's totally fine. Or if you think of something later on, I will give you my contact information. You can also email sales. Not sure where the slide went, but if you email sales@essentium.com for more information. Technical difficulties, of course. Yeah, you can email sales@essentium.com, or you can email me directly at leslie.bush@essentium.com. leslie.bush@essentium.com. All right. Well, I want to thank all you guys for your time. I won't hold you up any longer. Thank you for tuning in, and stay tuned for the April webinar on conformal masking. Thank you, and have a good day.